Okay, so today we're diving into something that sounds deceptively simple, but as always, I have a feeling it's going to get really interesting. Close packing of spheres. How to pack spheres together in the most efficient way possible. Like imagine you've got a box of ping pong balls or oranges in a crate. How do you fit the absolute most in? So, we're going to unpack some seriously cool geometry in this deep dive, make some unexpected connections, and even get into some real world applications. Okay, I'm ready to have my mind blown. And we've got an expert standing by to help us do just that. So, one of the first things that jumped out at me from the excerpts you sent was this term, rhombic dodecahedron. It's a mouthful, I know. What is that exactly, and why is it important in the context of close packing?
It is a mouthful, you're right, haha.
Mm.
So picture a 12-sided figure, kind of like a cube, but more complex. And the cool thing is, if you connect the centers of perfectly packed spheres to their 12 nearest neighbors, you actually start to see these rhombic dodecahedrons emerge, like they're the hidden scaffolding of this incredibly efficient packing structure.
Okay, so already we're seeing how this simple idea of packing spheres starts to get complex pretty quickly. And speaking of which, the excerpts mention both square and hexagonal arrangements of spheres. Are these two different ways of achieving close packing, or is there something more going on?
It's easy to think of them as different, but they're more like two sides of the same coin. Imagine you've got a square arrangement of spheres. Now rotate that arrangement. What do you see? The hexagonal pattern starts to emerge. They both ultimately describe the same incredibly efficient close packing of spheres, or CPS.
So nature loves efficiency, right? Which is probably why we see close packing pop up everywhere. It's not just about ping pong balls and oranges, is it?
Absolutely not. CPS is nature's way of optimizing space, plain and simple. We see it in the arrangement of atoms and crystals, the way cells pack together in a beehive, even how pomegranate seeds fit so perfectly together. It's all around us.
Wow, okay, we're going from ping pong balls to the structure of the universe here. That's quite a deep dive. And speaking of going deep, the material mentions something called periodicity. What does that mean in this context, and why should we care?
Yeah, periodicity is key here. So think of it like this. Imagine a stack of pancakes. Sometimes the pattern repeats every other pancake, right?
Hmm.
And sometimes it repeats every third pancake. It's similar with CPS. Square arrangements, they have a periodicity of 2, meaning every other layer is the same, while hexagonal arrangements have a periodicity of 3.
Okay, so we're talking about these repeating layers, almost like planes within the overall structure. And that's where I stumbled upon this other mention of orthogonal and tetragonal axes. It's like we're moving beyond basic geometry now. Help me out here.
Right, so we usually think of space in 3 perpendicular directions: length, width, height, like the edges of a box. That's our orthogonal system. But with close packing, particularly the hexagonal kind, we actually unlock FUR additional axes. Because of the way the spheres touch at those specific angles, it's a whole other level of understanding space.
So you're telling me the simple idea of how spheres are arranged unlocks a hidden dimension of geometry.
Exactly. And it's more than just some abstract concept. These axes and how they divide space, it actually helps explain why certain materials have the properties they do.
Hold on. Are you saying that how spheres pack together can actually influence a material's strength, for example, or its conductivity?
Exactly. It all boils down to how those atoms, those tiny spheres, arrange themselves at the most fundamental level.
This is blowing my mind. So just by rearranging the atoms in a material, we could potentially make it stronger or a better conductor of electricity. Are there real-world examples of this?
Absolutely. Take carbon, for example. You've got graphite, which is soft and slippery,
Mm.
and then you've got diamond, one of the hardest materials we know. And the difference, it all comes down to how those carbon atoms are arranged. Different types of close packing. Vastly different properties.
That's incredible. It's like we've been talking about geometry this whole time, but we're really talking about the building blocks of the universe and how they interact.
Exactly. And it gets even more fascinating from here.
Oh, no, you can't leave me hanging like that. What else does this close packing idea unlock?
Well, it goes beyond just simple arrangements, you see. The material you send, it mentions platonic structures. You know, those perfectly symmetrical shapes,
Yeah.
cubes, tetrahedrons. Turns out, by connecting the centers of close-packed spheres, we can actually build these very structures.
Wait, hold on. You're telling me that those perfect platonic solids, they emerge from how spheres pack together? That's wild.
It is. Think of it this way. The spheres are like the building blocks, and close packing is the instruction manual for how to create these incredibly balanced and harmonious forms. It's like we're uncovering a hidden code that governs the structure of the universe. And it all starts with a simple sphere.
Okay, this is officially way cooler than I ever imagined when we started talking about packing spheres together. This has to have some mind-blowing implications.
You have no idea. Just imagine the possibilities of understanding and harnessing this code, not just in nature, but in technology, engineering, even art.
So we're talking about unlocking the hidden code of the universe just by packing spheres together. That's pretty amazing.
It really is, and there's so much more to uncover. Remember those orthogonal planes we talked about earlier? They're crucial in understanding this whole square lattice arrangement of spheres.
Right, we talked about orthogonal planes being those slices through a perfectly stacked set of spheres, but how does that connect to this idea of a square lattice?
Okay, so imagine those spheres arranged in a neat grid, like a chessboard, that just goes on forever, infinitely, in every direction. That's your square lattice.
Okay, I can picture that.
Now slice through that lattice with planes, and all those planes are at right angles to each other. Those slices, those cross-sections, those are your orthogonal planes.
Yeah.
And where they intersect, boom, you've got the familiar XYZ coordinate system. It's the same system we use to understand space every day. Now we're seeing it through the lens of close packing.
Okay, so the orthogonal planes are like a way to see the order within this, like, simple square arrangement of spheres. But then the source material mentions tetragonal planes. What are those, and how do they fit into all of this?
Ah, yes, tetragonal planes. This is where it gets even more interesting. Remember how we said there are those two main ways to pack spheres efficiently? Square and hexagonal?
Right, like two sides of the same coin?
Exactly. Just as that square arrangement relates to orthogonal planes, the hexagonal arrangement leads us to these tetragonal planes.
So are we slicing our sphere cake into, like, hexagons instead of squares now?
You got it. These tetragonal planes, they cut through the close packed structure in a way that highlights that hexagonal pattern. And here's the really cool part. Instead of just those three perpendicular axes like we see with orthogonal planes, we end up with four axes that are equally spaced and intersect at the same angle. It's a whole different way of dividing up and understanding space.
Okay, so just to recap, we've got orthogonal planes and axes for the square arrangement, and then tetragonal planes and axes for the hexagonal arrangement.
Yeah.
It's like unlocking two different but equally awesome ways of looking at the world of close-packed spheres.
That is a great way to put it. And this is where it gets truly mind-blowing.
You got to tell me more. Don't leave me hanging.
Well, the source material, it mentions how each sphere in a close-packed arrangement, it actually belongs to an infinite number of planes and lines.
Hold on, infinite. How can something be a part of an infinite number of things? My brain's starting to hurt a little.
It's because we're not limited to just those orthogonal and tetragonal planes we talked about. We can imagine slicing through this close-packed structure at an infinite number of angles, revealing countless planes, each containing our sphere.
So we're not just talking about a few basic arrangements anymore. We're talking about this whole crazy web of connections and possibilities, and it all comes back to efficiently packing spheres together.
Exactly. And that, my friend, is where things get truly profound.
Okay, now I need you to explain this like I'm 5. What's so profound about an infinite number of planes? Help me see the bigger picture.
Okay, well, it suggests that even within just our normal three-dimensional world, there's this hidden depth and complexity that we just don't always see. Close packing of spheres, it's not just about geometry. It's like a window into the fundamental nature of space itself.
Wow, that is kind of profound when you put it like that.
It makes you wonder, what else are we missing? What other hidden patterns and connections are just out there waiting to be discovered if we just look at things a little differently?
This is definitely making me see the world in a new way.
And this is really just the tip of the iceberg. There is so much more to uncover about close packing and all its implications.
You know, this whole deep dive has been like falling down a rabbit hole. Like we started with packing spheres, and now we're talking about the infinite nature of space. It's pretty wild.
It really is. It just goes to show that even the simplest things can be mind-blowingly complex when you look at them the right way.
I have a feeling I'm going to be seeing clothes packing everywhere I go now. Like stacks of oranges at the grocery store or the pattern in a honeycomb.
You probably will. And you know what's even cooler? Close packing, it's not just limited to nature. We see it reflected in things humans have created too. From ancient architecture to like modern nanotechnology, it's everywhere.
Now that you mention it, I've always been kind of mesmerized by those geodesic domes. Are you telling me those are based on close packing too?
Absolutely. Geodesic domes with all those interlocking triangles, they're like the perfect example of how strong and efficient close-packed structures can be. They distribute weight evenly and can enclose a huge amount of space with the least amount of material.
That's incredible. It's like we've been intuitively tapping into this principle for centuries without even realizing it.
And as we understand close packing even better, who knows what other applications we'll find for it. The possibilities really could be endless.
Well, this has been an amazing deep dive. I mean, we went from packing ping pong balls to unlocking the secrets of the universe, and it all comes back to this elegant idea of close packing.
It just goes to show sometimes the most profound discoveries are right in front of us. We just have to know what to look for.
Well said. And to everyone listening, we hope this deep dive has inspired you to look a little closer at the world around you. You never know what hidden patterns and connections you might find. From the tiniest atom to the vast expanse of space, the universe is filled with wonders waiting to be discovered. And on that note, we'll wrap up this deep dive into the fascinating world of close packing. Until next time, keep exploring, keep questioning, and keep those curious minds of yours wide open. We'll see you in the next episode.